In our last talk, we started talking about infinite series, and infinite series are going to turn out later in this chapter to be really important things, and so if we're going to be real interested in whether they converge or diverge, because if they ended up diverging, they are of little value. If they go off to infinity or if they don't converge to a number, they're not going to be very helpful to us. So we started to learn a couple of things about whether a series converges or diverges. And we're going to be looking at, for the next couple days anyway, series that all have non-negative terms, zeros or positive terms. Later on, we'll see what happens if we start getting negative numbers in there. So, to begin with, we've got a series like this, which looks kind of complicated, but we learned a test called the Nth Term Test, which if you took the limit as n approaches infinity of the nth term of the series, so this would be the nth term of the series, if that doesn't go to 0, we say the series diverges. Series a sub n equals 1 to infinity would diverge. And if we look at this, if we're taking the limit as n approaches infinity of this term, we can ignore the 50, we can ignore the square root of n because they're lower powers of n, and we can see that that would converge to 1/100th. Well, it's close to 0, but it's not 0. So by the nth term test, we could say that this whole series diverges. Now we have to be careful because this test only goes one direction. In other words, for convergence, it's necessary condition that the limit of the nth term goes to 0. It has to go to 0. That's a necessary condition for convergence. That's what this is saying. But it's not a sufficient condition. In other words, just having the limit go to 0 doesn't mean that it converges. And we showed in the last talk that if we took 1 over n, 1 plus a half plus a third, that one ended up diverging even though the limit as n approaches infinity of 1 over n does go to 0. So that's usually the first test we're going to look at. Then we looked at a special type of series, that this is one of them, an example, where we have a r to the n. So say we start out at 0, r to the 0 power would just be 1. So you get a series that looks like this. And you can see to go from one term to the next, you keep multiplying by r. And this is called a geometric series. And we proved that it converges whenever r is less than 1 in absolute value. So between -1 and 1, not including 1. And not only that, but we said it converges to a over 1 minus r. We proved that. We didn't just say it, we proved it. If r happens to be greater than or equal to 1, then the geometric series would diverge. So we could say that this one, the first term, well, the r is 1/3. If we multiplied this out, we get 5 plus 5 over 3 plus 5 over 9. So the first term would be 5, and the r would be 1/3. So this would converge to 5 divided by 2/3, or 15 halves, or 7 1/2. So geometric series are kind of nice. It's really easy, if you recognize them, to know whether they converge or diverge, and if they happen to converge, we can even figure out what they converge to. So they're kind of special. But there's a whole lot of other series, and so we need some more tests. So one kind of important test is the comparison test. So we're going to take a series A sub n, and I'm just going to write it like that. It really means n equals 1 to infinity, or 0 to infinity, or 2 to infinity. It doesn't really matter, but I'm talking just here about an infinite series. So say I'm trying to find out whether that converges or diverges. And say I know two other series. I know that this series diverges, and say I have another series that I know converges. So I can say that the series A sub n converges if the values of A sub n are less than the values of C sub n for all n greater than some big number n. So basically what we're saying is the first big N terms don't really matter as far as convergence goes. The first 1,000,000 terms are going to add up to something. It's what happens after that that really is important. So no matter what happens in the first big N terms, whether that be 1,000 or 1,000,000, if once you hit that point, if all the rest of the terms our values that we're trying to find out about are less than or equal to all the values in this convergence series, then we can say that this one converges also. I hope that kind of makes sense to you, because to get a series to converge, we look at the sequence of its partial sums. So this would be adding up the first n terms of our series. Well, if you look at the first n terms, big N, that's going to equal a number. And also, if this other series converges, the big N plus first term on, all the way to infinity, must go to a number. So that means the series we're looking for, its partial sums are all going to be bounded by whatever those two numbers add up to. So it's always going to be bounded from above. And if you have a sequence of an increasing sequence, which these partial sums are always going to be increasing because they're all positive terms, if it's bounded above, then it has to converge to something. Maybe not that number, but to some number. Anyway, if we have another case, we could say our series that we're trying to find out about diverges if all the terms A sub n are greater than or equal to D sub n, where D sub n is a series that diverges. And I think that, again, only has to be true for n greater than n. So what we're saying is that we have a series of terms, when you add them up, that go to infinity, and our terms are even larger. So that means it certainly has to diverge. So that even makes more sense. Now, what does this allow you to do? Now, if we know whether a series converges or diverges, and we can compare it to the one we're looking for, we can make a decision. Now, where would that work? Say you were trying to take 1 over n factorial. which is 1 plus 1 over 2 factorial plus 1 over 3 factorial, and it keeps going on, what could I compare that to? Well, I don't know too many things, but I do know geometric series. So if I could compare that to a geometric series, so say we took 1 over 2 to the n, which is 1 plus a half plus 4th plus an 8th plus a 16th. You can see for a while these terms here, well, especially once you get to very big numbers, these terms are a lot smaller than these terms. And we know that this is a geometric series with r equals 1/2. So this one's going to converge, and these terms, once you get here, you know, the next term, 1 over 6 factorial, is going to be 1 over 720. So that's a really small term. So you can say, who cares about the first few terms? We know that in general, that this one converges, therefore that one converges. And all you'd have to do is say by the comparison test and show that after a certain amount, these terms are term by term smaller than the one we're comparing it to. And I'll do a few more examples in just a little bit. First, we're going to talk about the integral test. So, if we have a series a sub n, and say we have also a function y equals f of x, such that f of n equals a sub n. So all the integer terms of the function f are the same as the terms of this series. Then what we can say is the integral from 1 to infinity of f of x dx and the series, the summation n equals 1 to infinity of a sub n, either both converge or both diverge. So whatever one of them does, the other one does. So if we can know, if we're trying to find out whether a series of ours converges or not, we can just look at the integral. And they're going to do the same thing. They don't necessarily converge or diverge to the same values, but they either both converge or both diverge. Well, we better prove that. So here's a function y equals f of x. And we're going to assume that that distance right there is called a1. And this is a2. So we have a series a sub 1 plus a sub 2 plus a sub 3 all the way to infinity. So if this distance is a sub 1 and this function is y equals f of x, you see it satisfies what I just said here. F of 1 equals a sub 1. There's a sub 1, this is f of 1, and it works on all values of n. So what happens then if I make these rectangles all the way down? What's the area of this first rectangle? It's a1 times 1, or a1. This next rectangle right here, the height is a2 and the width is 1. So we have a1, this rectangle is a2, This is A3, and then this last one right down here is A sub n. So if you add up all those rectangles from k equals 1 to n, that's what you're going to get if you add up all those rectangles. And you can see that this is the nth partial sum of this series. And what can we say about that? Well, look at this integral. If you take the integral from 1 to n plus 1, you can see that the area underneath the integral is less than under these rectangles. So I can say the integral from 1 to n plus 1 of f of x dx is less than this summation. Now, let's go over to this one and do it slightly different. That's still going to be A1, but now let's make the rectangles in the other direction. Now, that's A sub 1, that's A sub 2, A sub 3, and this last one is A sub n. So if I add up all those rectangles, I'm going to get this same thing, and you can see that all the rectangles are below this function. Of course, I'm only going from here. So if I take A1 and add the integral from 1 to n f of x dx, if I take A1 plus the integral, the area underneath this curve from here to here, I can see that that's going to be greater than this summation here. So what do we have? This right here is the nth partial sum. So if the function f of x, the integral from 1 to infinity, if that converges, then we can say, even as n approaches infinity, our nth partial sum is less than whatever this converges to. So this is going to hit some type of limit. And if the integral from 1 to infinity of f of x dx, if that diverges, we can see that our nth partial sum is going to be greater than that. So there isn't going to be a limit as n approaches infinity of our nth partial sum. So this is a proof of the integral test. So if I can just take any series and turn it into an integral, I've got a test that's bound to work. So the only problem with integral tests are, a lot of times when you actually take the integral, it's not easy to do. So going back to here, we could take the integral from 1 to infinity of this function, but that's a pretty hard integral to take. So it's a foolproof test if you can take the integral. Now, the real value to this test probably is to deal with one type of summation. N equals 1 to infinity of 1 over n to the p. This type of series has a special name. It's called a p-series. And what do we know about that? Well, we can use the integral test. What is this going to look like in an integral? It's 1 to infinity of 1 over x to the p dx. Well, when we did the video on improper integrals, we proved that that converges if p is greater than 1. That means this is going to converge if p is greater than 1, and we proved that this diverges if p is less than or equal to 1. You remember when we did the integral from 1 to infinity of 1 over x squared, when p was greater than 1, that only turned out to be an area of 1. When we took 1 over x, or 1 to infinity of 1 over x dx, it diverged to infinity. So we can use the same thing for a p-series test. Anytime we get 1 over n to the p. So let's try to do a few problems with the tests that we know so far. Okay, number 1. If you just rewrite this as 1 over n to the 1/3, our job is done. This is now a p-series. It's 1 over n to the p, and p is less than or equal to 1. So I can say p-series with p less than 1, the series diverges. If you have to write a reason, that's a perfectly good reason, because we've already proven that. Now, here's one that looks a little bit more complicated. But realize that every term here has a million in it. A million times something. That's not going to really affect the convergence or divergence. I could take this and take it right out front. So then I just have a million times what this series converges to, if it converges. And what do we have here? We have a million times a series n equals 1 to infinity, 1 over n to the 3/2. Well, we know that this is a p-series again. It's 1 over n to the p, but this time p is greater than 1, so therefore that series converges. And a million times something that converges is still going to converge. So this one converges. And you could just say it's a million times something that we know converges because it's a p-series, p greater than 1. Okay, again, does this look a little bit like a p-series? I think you're starting to see why this p-series test that we proved is so important. Because a lot of series look very similar to p-series. Well, this time it does, except it's got that sine squared of n up here. So now we're going to use two of our tests. We're going to use the p-series and we're going to use the comparison test. We're going to compare this to 1 over n to the 5/3. We know this is a p-series with p greater than 1. So this one converges. And since we know the sine function never gets bigger than 1, we know that these terms right here are term by term less than these terms. So by the comparison test to a p-series test so that we know converges, we can say that this series converges. And it is kind of important to know that this is sine squared of n, so all the terms are going to be positive, so we can really use the comparison test. Okay, this one looks a little more difficult. I know that the series 1 over n is a p-series with p less than or equal to 1, so this diverges. So you'd say, maybe I can use the comparison test. But now, when you're adding numbers down here, you're multiplying n by natural log of n. And those numbers mostly are going to be bigger than 1. So you're making the denominator larger, so these whole terms are smaller. So maybe they're enough smaller that it's going to make it converge, even though this one diverges. We don't know for sure, but we can't use the comparison test. So what we can do, we can always try the integral test. So let's try to convert this into a function and see if that one converges or diverges. You remember how we do improper integrals. We make this the limit as t approaches infinity, and you take the integral from 2 to t, and I'm going to write this 1 over x dx divided by the natural log of x. So if you think of this to be u, the derivative is up at the top. So we have it in the form of du over u. So you get the natural log of the natural log of x from 2 to t, and then you're taking the limit as t approaches infinity. Well, the natural log of the natural log of t, as t approaches infinity, this is going to go really, really slowly to infinity, but it's going to eventually get there. It keeps growing and growing. So since this integral diverges, we can say that that series diverges. So there's a use of the integral test, besides what it did is for the p-series test. Okay, so just a few more here. This one, I changed the n to a k. There's nothing special about the letter n. If it really bothers you at the beginning, you're always allowed just to do that. And does that look a lot like a p-series? It looks a lot like 1 over n. And we know that this diverges. So we have to see, can I use a comparison test? Are these terms larger than these terms? And yes, because of that minus sign there. If I make the denominator smaller, it makes the whole fraction bigger. So that means term by term, these are bigger than this, and this diverges. Therefore, by the comparison test, this is going to diverge. You're using the comparison test and the p-series test. You're comparing with a series that you know whether it converges or diverges by the p-series test. Now, here's one that's fairly similar. And just for kicks, I started at 10 instead of at 1. Remember, those first terms don't really matter as far as convergence or divergence is concerned. Well, I'm going to compare that to what? 1 over n squared. We know that's a p-series with p greater than 1. So this converges. And what do I see here? Those numbers, those fractions, are smaller than these fractions because you're making the denominator bigger. So again, we're allowed to use the comparison test, and we can say that this one converges in comparing it with this series, which we know converges. So we can say converges. Now, just to show you something, could we do the same thing for 7 as we did for 5? Let's turn it into n just to make you more comfortable for right now. We can't really compare this to 1 over n because this diverges, yet these terms are smaller. So we're kind of stuck at this point. We don't really know one way or another. And similarly, if you compare these two, I can't really compare this one to 1 over n squared because this converges by the p-series test, but these terms are bigger than these terms. So we've got an incentive to learn new tests. Maybe we would like to compare this in both cases, but we can't quite. So maybe in the next talk, we'll learn a new test that'll take care of that situation. So good. Have a good day.